Hello, welcome to this video. Today I'll show you a tutorial about a PET-CT scan, which is a dynamic scan, so it's 4D data. You can load it here under the tutorial button, under SPECT, PET-CT dynamic, load the example dataset, and then you can inspect it in 3D here and rotate it around. And let's hide the segmentation for a moment. And you see here the CT scan, but also the PET data here. This is from the first time point. And you see the FDG in the vena cava right after injection. And now we can go through the time mouse mode here, this one, but we need to select the overlay because only that is a 4D dataset. And now you see here in the toolbar of the time mouse mode, you see here the time points, 37 time points, and you can go through them by clicking here. And now you see the tracer here distributing through the mouse body. You can also use the mouse here to move it, and you can quickly go through the time points, and you see it here in the kidney medullas, and it ends up in the bladder. And you see some accumulation happening in the myocardium and the eyes. So let's go to the end. The last time point here, you see a strong signal in the myocardium, which is typical for FDG because it's a surrogate for sugar, and the heart is a beating muscle. Even if the mouse is anesthetized, the heart is still beating, so it consumes sugar, glucose. Now we have a segmentation here. This was loaded with a tutorial, and I'll delete it now and create some segmentation again. So let's jump here to the torso. So we see the heart here, and we can use the ISO tool here and add a class heart and click somewhere, and then we get this myocardium. We can jump here to the bladder, add a class bladder, and do the same for the bladder and for the kidneys. So let's actually go to an earlier time point where we have the medulla appearing right here, and let's use the ISO tool to segment the medulla of the two kidneys here. So in 3D now we have these kidney medullas both. Now we can go to a later time point and get the kidneys here also with the ISO tool. Just it's a little bit of a bigger region, and we can get the eyes here. And we can go to the first time point to fetch here the vena cava and call it AIF for arterial input function. Now we have that. So we have a few regions here, and we can get the region class statistics with this tool here, and this shows you one big table, and we now have one row for each organ, for example the heart, and each time point. And you can check at the graphs here. So this shows you the time activity curves here. You see that a lot of it ends up in the bladder here, but we have this interesting peak here at the medulla due to the renal elimination, and a lot of ends up in the myocardium, and you see a little bump here early in the AIF for the blood pool contrast. And what's also interesting here we have a unit, kilobecquerel per cc, and this is the voxel unit of this volume of this data set, and that was loaded from the DICOM as metadata. There was even more metadata loaded. You can check it here under the nuclear menu, under SUV calibration or %ID per ml calibration. And there you can check which other metadata was loaded that is relevant for this, and that is the injection dose here and the injection unit. Sometimes it's also entered as millicurie. And the voxel unit here was found, but also here the scan time was loaded and the injection time and the isotope and the weight of the mouse. And from all this information, a certain factor is computed. So if I change the weight here, you will see that the factor changes. And this is a scale factor that is applied here. You can apply it by clicking apply to convert to SUV, standard uptake value, which is a more intuitive unit. And we can look at the statistics now. The curves have the same shape, but the value is now in SUV here. And if you can save this overlay now, it has a different voxel unit, but you can go back also with clicking undo. Now we are back at this unit here, and let's try converting it to %ID per ml here. It's a similar dialog as the SUV dialog, but the weight is actually not required, so let's apply it. And now we have a voxel unit of %ID per ml, and in the table you can also see here this the mean concentration in %ID per ml, and the total here also in milli %ID. These numbers here, by the way, they are in German notation, so it's the comma is actually a decimal point, and it'll use a decimal point if you use it in with the English settings of the operating system. Okay, I hope this helps. Thank you. Bye bye.